Hello, everybody, and welcome back to day 2 of Python WebConf 2021. My name is Josh Qualls. I'm the Loudstorm account manager here at 6 Feet Up, and I'm really glad to be joined by Ben today to talk about cloud parallelism with serverless on AWS.
All right, well, thanks for having me, everybody. My name's Ben, and today we're going to be talking about cloud parallelism with serverless on AWS. As I mentioned, my name's Ben. I'm the VP of Engineering at Theodo, a company that helps other people build and run digital products. And I'm also an AWS serverless hero, meaning I get to speak at conferences like this and write and talk about serverless quite a lot. You can follow any of the stuff I do on Twitter at Ellerby Ben. And I also run the Serverless Transformation blog, podcast, and newsletter. All the links to sort of the open source content you can find on the Theodo website at theodo.co.uk/experts/serverless. Now, before we jump into the parallelism part of the talk, I just want to focus on serverless to start with. Some people might be less familiar with serverless, and serverless is one of those terms that means different things to different people. To me, serverless is an architectural movement. It allows developers to build and run applications without thinking about the underlying servers. Developers can send application code, which is run in a completely abstracted way from them. And it's also the leveraging of third-party services to take further abstraction. Things like Cognito for identity as a service or Okta would be another example outside of AWS. There's also a framework with the same name, the Serverless Framework, which is a really great infrastructure as code solution for serverless architectures. It does make talking about serverless a little bit confusing. Today, we're mainly focusing on serverless, the architectural movements, although there will be a couple of code examples using serverless, the framework. Now, why do people take a serverless approach to building applications? Well, first of all, there's a cost reduction. The pay-per-use model of serverless services means that when your application isn't doing anything, you're not paying for it. Also, there is less ops that's needed to build and support applications. It's not no ops, so there's still definitely a need for ops, but it's slightly different, the work that they do. It's not patching servers with security updates, it's more managing a distributed system. But through this, we get to reduce the total cost of ownership of running applications, which can massively empower an organization to save a lot of money and invest it in more innovative endeavors. It also allows developers to focus on delivering business value as they're no longer writing code to run infrastructure. Instead, they're writing the actual code, which is the business value of that organization. These architectures are scalable from day one and completely elastically scalable. And finally, as we start to make more efficient usage of the resources in our data centers, we can actually reduce the CO2 impact of running applications as we start to reach a critical mass of applications built in this way. Now, Lambda is sort of the poster child for serverless. It's the function as a service that comes from AWS. Other cloud providers do exist, but Lambda is sort of the poster child. It's the classic service when we talk about serverless. Lambda allows us to send a piece of application code, which is run at a different runtime, depending on the language you want to use, and it's run in response to different events. And we'll come to talk about what those events are in just a moment. In terms of runtime, Lambda at this point supports Node, .NET, Go, Ruby, Java, and also custom runtimes. So through a Lambda layer, or as of December last year, we can now use a Docker container. We can use quite a variable number of languages inside of our Lambda functions. I once ran an application fully on PHP on Lambda for a particular client. I would not recommend doing it, but it is definitely possible. But of course, the focus of this talk is going to be the Python runtime, and Python 3.8, 3.7, 3.6, and 2.7 are all supported by default, but you can also ship other versions and sort of other modifications as a custom runtime if needed. So when we talk about Lambda, we typically talk about functions. We have Lambda functions, and these require us to have a handler function, which is a function of code that will be run in response to a different event. Now, a handler function typically will have these two inputs, an event and a context. The event will be the body of that event, so potentially some data that's been sent through, for instance, through a REST API call. It could be the body of a post request, and also some context as to why this event has been triggered and some metadata around that. We can then return some value, and then that will be returned to the source of that event, be that an API gateway REST request or a different event trigger, which we'll see in a moment. As we start to build more complex versions of this, we can pull out different elements from that event object, do some string interpolation, return a message. And that kind of sort of highlights what a Lambda function is. A Lambda function has a handler function, which is a function of your code, which is triggered by AWS when Lambda is invoked. Now, if we want to go and deploy that function, we could go and click through on the AWS console, but with a move to serverless is really a move to infrastructure as code. And as I mentioned earlier, the serverless framework is really great abstraction on top of CloudFormation for AWS. To use a serverless framework, I know it's a Python conference, so this doesn't look too good, but it works really well for deploying Python environments as well. We can npm install -g serverless and then run serverless creates --templates AWS Python 3 -- path, and that's just a directory. So we're just sort of taking a boilerplate Python application and generating a serverless context around that. So we have the serverless.yaml, which is our infrastructure as code file, and we also have our handler.py, which contains a very simple handler function. By default, this handler function would look like this. So we have our event and our context. We're building out a message, a body, and then we're turning a response with a status code. So ideally, we're going to then go and trigger this via something like an API call, which will then get that status code and body back as a JSON. If we look at the serverless.yaml that's been generated, it's got a very simple service name, which can be anything you want, really. The provider, so AWS. Again, the serverless framework can run across different cloud providers, which can be quite useful. And the runtime of Python 3.7. Inside of there, we've got our functions, which are our Lambda functions. We've got the hello function, which is going to have a handler, and that's the handler file.hello, which is the hello function inside of that handler file. We can then use the serverless framework to invoke that function locally. So SLS, the serverless, invoke local -f hello. So we're just going to run that function locally on our computer. And then if we want to go and deploy that, we can run SLS deploy. We'll have to pass it a IAM policy to allow it to be able to deploy. But for now, let's just ignore that complexity. And then we can run SLS invoke -f hello. And then we're going to actually invoke that Lambda function through the AWS SDK, and it will trigger that in the cloud and send the response back to our local computer. And there's quite a range of things that can trigger Lambda functions. It can be a classic example of API gateway, which is triggering, sort of routing an API request through to trigger the Lambda function and sending the response back. It could be in response to a service like Cognito, the identity as a service on AWS. Potentially users reset their password. We want a side effect, so we can trigger a Lambda function to go send an email. It could be Lex, it could be DynamoDB when an object's written to that database. It could be Event Bridge, which is a way of building sort of event-driven applications that I actually spoke about at this conference last year. It could be Kinesis. There's really a large number of triggers for Lambda functions, which enable us to build quite powerful applications. Now, I've talked about Lambda quite a bit, but Lambda is not serverless. Lambda is one example of serverless. Inside of AWS, there are many other serverless services. So there's S3 for storage. DynamoDB is a completely NoSQL serverless database. API gateway to proxy API requests through to Lambda. Cognito for identity as a service. SQS is a queuing service. Step functions to orchestrate workflows, as we'll see later in this talk. And Event Bridge, a service that I spoke about last year, about how you can build a completely serverless event bus to drive your microservices. And there are many more serverless services inside of AWS and other cloud providers. So from this, we can build out our serverless microservices. And if you want to see a sort of more real world example of what a typical serverless architecture looks like, you can feel free to go to medium.com serverless transformation. And on there, there's what a 100% typical serverless architecture looks like. But for the rest of this talk, we're going to focus more on the parallel aspects of building with serverless rather than the generic aspects of how we can build serverless microservices. So for today's talk, we're going to focus on two particular services: Lambda, that sort of poster child for serverless, and Step Functions, which allows us to orchestrate serverless and other services inside of AWS. If we focus on Lambda to begin with, here are some of the key characteristics of Lambda as a service, which have been updated as of this year. So in terms of memory, we can go from 128 megabytes to 10,240. In terms of timeout, it's limited to 900 seconds, which is 15 minutes. Burst concurrency, we're going to dig into in a moment, but that's how we can handle traffic spikes. The temp directory, which is the only place you can write to disk on Lambda, is limited to 512 megabytes, although there is now support for EFS, and you can also write to S3 as well. And concurrent executions, the interesting part for this talk, by default limited to 10,000 to 1,000. But that's a soft limit that can be raised to quite a high degree on AWS by raising the support tickets. So what if we have a task that takes longer than 900 seconds? Well, if we take an example of an application I was building a couple of years ago now for a client, they had a report system where they could generate these sort of web reports using React and JavaScript graphing library, and then they could then save those out as PDFs for compliance reasons. And these were very long reports, lots of graphs, lots of statistics, and really for compliance reasons. No human was ever going to read these reports, thousands and thousands of pages long. To sort of build these reports, they were using Chrome in a headless context to be able to go load that page up, save it out as a PDF, and write it to somewhere. So if we think about the sort of serverless approach to this, we have sort of a legacy server that's serving up this web page. We have a Lambda function that's running a headless function of Chrome using something like Puppeteer, which is the Python version of Puppeteer. We can then load that web page, export it as a PDF, and then drop it into a serverless storage system like S3 on AWS. Just a quick side note before we keep going on this PDF example, and it'd be quite useful as we start to scale this out. When a function is invoked, AWS Lambda creates an instance for that function, which runs the handler method and returns the response. That sort of function instance remains active, waiting to process more events. And if a function is invoked sort of twice in a short period of time, so it's invoked while it's already, one instance is already answering one request, it will spin out another sort of Lambda instance to handle those two requests concurrently. And this is where we start to get some concurrent aspects of Lambda. When a Lambda sort of instance is started for the first time, there's a cold start time, which is massively reduced over the last few years. But basically in that step, we're downloading the code, which is our application code. We're starting up the container and bootstrapping the runtime. Subsequent invocations of that particular function instance will then have a much faster start time, or a faster start time at this point. And we call those warm starts, where we just need to start the code. We don't need to download the code and start the container and the runtime. In terms of concurrency as well, just another side note, concurrency is a number of instances that serve at a given time. So if we have a Lambda function, it can have a number of sort of function instances, and the number of those that are up at a concurrent time at the same time is the concurrency. When we have a traffic spike in an application, the sort of cumulative concurrency is limited by the burst concurrency quota. So there's a limit to how fast we can ramp up. If we see the graph on the left, we can see we're ramping up quite quickly, and then we've hit our burst limits, and we're ramping up less quickly, but still at quite a rate. After we reach our concurrency limits, we then increase at a rate of 500 new function instances per second. And that overall concurrency is limited by our concurrency limit, which I mentioned before is a soft limit that can be raised. And it's really interesting to look at provisioned and reserved concurrencies as more advanced topics on how you can manage concurrency of Lambda. But let's jump back to our PDF example. Now we have a bit of knowledge on how concurrency works with Lambda as a service. So I mentioned before, we've got that cold start and warm start. But then we're going to have to spin up the browser, load the web page, generate the PDF, and upload that PDF to S3. Now, those boxes in red are the boxes that are going to scale somewhat proportionally to the length of our document. And actually, as our document increases to quite a degree, the browser starts to take a really long time to just even load up the web page. The PDF generation starts to get really slow and crashes out. And that upload is sort of linked to how big the file is to get across on the network. So what if we could handle this differently? What if we could take a concurrent approach? We could chunk up the reports into different sort of PDFs, write them to S3, and then have a job that collates them back into one PDF document, which actually proves to be more efficient in our example. Well, it looks quite an interesting architecture, but there's quite a lot of Lambda functions and quite a lot of different steps happening. So we're going to need some sort of service to orchestrate that process. And this is where another serverless service, which is really growing in popularity at the minute, Step Functions, comes in. So Step Functions is a serverless function orchestrator that makes it easy to sequence AWS Lambda and other multiple resources of AWS into applications. So it doesn't all have to be Lambda in every step, but in our example, we're only going to be using Lambda in our step function. A step function is really the state machine. If you're familiar with state machines, we have a start and an end state, and then a number of transitions to intermediary states between there. And there are a number of different state types that we can have, a task being a Lambda function, but we'll see in a minute there are other state types or transitions that we can have in our step function. Going back to infrastructure as code, as I mentioned before, most serverless architectures make extensive use of infrastructure as code. CloudFormation, which is sort of the default infrastructure as code on AWS, has support for step functions, but it's really quite verbose and quite, they get quite long, especially as your step function starts to get nested. There's a really great plugin for the serverless framework called Serverless Step Functions, which enables us to have a much more abstract definition in YAML. So we have step functions, a state machine, my state machine, the name of it, the definition, which includes a comment about what it does, but then the states. So we have hello world, which is a task, which is going to run an AWS Lambda function, and that's also happens to be the end states in this very simple example. The use cases for step functions are quite varied. So it can be for sort of basic function orchestration. So we have one function giving the input to another function, to the input to another function. It can branch out on some decision based on the input. So basically an if condition. It can involve steps of human approval. So it could be, a driving license is uploaded, and then there's a human approval step to approve that driving license. It could be error handling. So when a Lambda function fails, what is the next step? How do we deal with that failure? Parallel processing, so what could we do with taking the same input and doing it multiple times? Well, the interesting part for us, dynamic parallelism, which is handled by map, which allows us to take an input array and trigger off a number of different workflows from that. So the map state runs the same set of steps for each element of an input array. So we can give it an array of values, and it will run the same set of steps on all of those. It requires an iterator, which is an object defined in the state machine to process each of those elements. So here we can see this is the map state. This is the iterator that's going to take an input array and run the same set of steps on every element of that input array. The input path is a location of that array. So from the output of this, in that output, where is the array that we're going to iterate over? And we can limit concurrency inside of step functions if we want to limit how many we have happening in parallel. If we think about our example of the PDF generation, we have a start state, then we have a task to generate chunks, which is going to be a Lambda function, which looks at the length of the reports. We were quite lucky in the fact that we could actually get the length of the report without having to load it up. But even if you did have to load it up, you don't have to generate the PDF, so it would still be faster. We can then split that up into a number of chunks. So here we've got chunks of 30 going from 1 to 30, 31 to 60, 61 to 90. That input array will be the item path. We then have a map state, which is a very simple step function that just has one task, which is the clone task, which is going to generate those independent documents. The output will then be the array of outputs from all the sort of invocations of that clone for all the elements of the input array, which is actually going to be the path to where that file has been written in S3. We then have a collate, which takes all of the written PDFs in S3, collates them together, and uploads the results. And then as our output, we have the bucket location, which is the result of the collated PDF. This massively brought down the number of crashes from really large PDFs that are being generated, but also reduced the time users are waiting considerably. We've seen sort of Lambda, we've seen how it can be used concurrently, we've seen how step functions can be used on top of that. But now let's look at another real world application of how we can use parallelism that comes from serverless. So load testing is a pretty typical requirement for architectures as they start to scale, and especially for serverless architectures, things like service limits can limit how our scalability works. And it's really interesting to sort of make sure we verify there aren't any missing of that sort of theory about how something can scale matches up with the reality. To take a real world example, last year I was working with a company called Gamercraft through Theodo. Gamercraft are a tournament for esports service. So they match players for tournaments on games like League of Legends. They're very spiky traffic because players play at different time. There are tournaments with cash prizes that happen, and then there are lots of players that need to be matched, and then the game's results need to be collated. In terms of architecture, it was completely serverless, so using Lambda, Step Functions, S3, DynamoDB, Cognito, API Gateway, Event Bridge. Actually, it's in the same manner that I spoke at the talk last year. It's using Event Bridge as sort of the central event bus between those event-driven microservices, which then fans out and sends events to things like the notification service, the user service, the match service, the team service, or the prize service. If we just look at the tournament service, for example, it's completely serverless, lots of Lambda functions, step functions, and Event Bridge. But what we want to do is really verify the scalability of the service through load testing. Now, typically with load testing, tools like Artillery are really useful in sort of simulating load and really useful for sort of validating that we can handle load that we expect. In Artillery, basically you define a scenario, so you give it a sort of target to hit against a number of phases with ramp ups. You can then give that scenario a flow, so post to the search endpoint, get this URL. And the really important part here is we're running Artillery run and then this configuration file, and then it's going to run that load test. But my computer can only scale so far, so we're going to have to try and get this across multiple computers if we want to be able to simulate the real scale of traffic that an application like Gamercraft was expecting. So where could we run this from? Well, we could run it from a server, as you've probably taken from the amount of times I've said serverless during this talk. I'm not the biggest fan of involving servers in my architectures. So what if there was a service that could run code without us having to think about or manage, being misspelled there, sorry, manage the underlying servers with support for massive parallel scale? Well, of course, Lambda is that service. And luckily, there is an open source project called Serverless Artillery, SLS Arts, which combines serverless and Artillery to get Serverless Artillery, which allows us to run our load tests from Lambda. And as you remember, Lambda can scale out to thousands of concurrent instances of that function, so we can get really high scalability in our load tests. Basically, how it works is we run Serverless Artillery from our computer. It then goes and calls Lambda. A Lambda then goes off and triggers a load of other Lambdas, which then go off and sort of attack for want of a better word, our target architecture. And then we aggregate the results of that load test. Importantly, run this from a different AWS account from the target architecture that you're trying to load test, because those service limits and things like Lambda, if your load test is already taking up 1,000 Lambda functions and your architecture needs to take up another 1,000 Lambda functions, you're actually going to be hitting your service limits faster than you expect. So running it from a different AWS accounts is a really key step here. We're given two examples that I've worked on personally, but I think it's also interesting to look at some of the other examples out there for how serverless and the parallel scale that comes from serverless is being used in the real world. So the UAE Mars mission is actually using serverless as part of its data pipeline for analyzing images. So it actually uses step functions to orchestrate Lambda functions in a very similar way as we saw, which then goes off and sort of looks over the indexes of a number of files, moving them over to S3, which can then be used by subsequent processing. I'll share the links to these slides. The article on this is really interesting, and the link is just at the bottom of this slide here. One final example, another real-world example, is the work that's happening with Neuron Bridge, which is a project to try and map the electron microscope and light microscope images that are doing neuron research on fruit flies. They're actually using step functions to sort of have a looping over, which is then querying DynamoDB, a serverless NoSQL database, enabling us to combine, or enabling them to combine a load of data and sort it before it then gets further processing. And they're scaling up to 3,000 concurrent Lambda functions to do this research. And that's all orchestrated by step functions with a massive operational load reduced, because step functions and Lambda are very manageable for those developers to work on. In conclusion, I realize we've gone through quite quickly, so we can always jump through some questions. Serverless is an architectural movement that allows us to abstract the complexities of building and running applications. Serverless is not just Lambda. There are many other serverless services that we saw at the start. And serverless services like Lambda have very high elastic scalability. They can get up to very high concurrency, but can also scale all the way back down to 0, which has some really interesting use cases, but also some challenges that your architecture needs to work around. Larger problems can and should be broken down into chunks that can be orchestrated by things like step functions. And not only are you going to reduce the time users are waiting, you also reduce the chance that things are going to time out, and you're going to have issues with memory as you start to break down these larger tasks into smaller chunks. I've been Ben. I'm the VP engineering at Theodo. If you want to reach out to me, feel free to contact me over Twitter at EllerbyBen. But otherwise, if you have any questions, I think you can drop them into the chat, and I think we can go through them now.